Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our peaceful journey through the science of rotation, if you find comfort in drifting off to the soothing rhythm of cosmic motion, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of the day lift from your shoulders. Tonight, we're going to explore one of the universe's most fundamental mysteries: why everything spins. From the smallest atoms to the largest galaxies, from the Earth beneath you to the sun above, everything in the cosmos is rotating, turning, spinning in an endless cosmic dance. We'll trace the story of how scientists came to understand this universal motion, each fact a gentle stepping stone in humanity's journey to comprehend the turning of the world. There's something deeply restful about rotation, the steady, predictable rhythm of things turning, the ancient patterns repeating endlessly. Over the next 100 facts, we'll walk this peaceful path together, discovering why planets spin, why galaxies spiral, why even you are turning right now as Earth rotates beneath you, carrying you through space at 1,000 miles per hour, though you feel perfectly still. There's no need to remember everything tonight. In fact, there's no need to stay awake at all. Let these words wash over you like gentle waves, each fact a soft ripple in the stream of discovery, carrying you peacefully towards sleep. Just allow the story to unfold at its own unhurried pace, the way the Earth itself turns, slowly, gracefully, following patterns laid down billions of years ago. Close your eyes now, and imagine yourself standing on a quiet beach at sunset, watching the sun sink toward the horizon. The sun appears to be moving, traveling across the sky from east to west, rising each morning and setting each evening in an eternal cycle. Our story begins here, with this simple observation that must have captivated every human being who has ever lived: the sun moves, the stars move, the heavens turn above us in a great celestial dance. For thousands of years, humans watched the sky turn overhead and drew what seemed like the obvious conclusion: the heavens were rotating around a stationary Earth. Stand anywhere on Earth and look up at night, you'll see the stars wheeling overhead in great circles, as if the entire celestial sphere were turning around us. In the northern hemisphere, all the stars appear to circle around Polaris, the North Star, completing one full rotation every 24 hours. It's a stately, majestic motion, so smooth and constant that ancient peoples built their calendars around it, tracked the seasons by which stars were visible at which times of year. The ancient Greeks, those patient observers of the natural world, developed sophisticated models to explain the apparent rotation of the heavens. They imagined a great celestial sphere, a giant globe surrounding Earth, with stars embedded in it like jewels in a crown. This sphere rotated once per day, they believed, carrying the stars, sun, moon, and planets in their paths across the sky. To them, the question wasn't why does everything spin, but rather what causes the celestial sphere to rotate. Some philosophers proposed that a divine force, the prime mover, was constantly turning the outermost sphere, and this motion was transmitted inward to all the inner spheres. Aristotle, the great Greek philosopher who lived in the 4th century BCE, developed an elaborate system of nested crystalline spheres, each rotating at different rates to explain the complex motions of the sun, moon, and planets against the background of fixed stars. In Aristotle's cosmos, everything had its natural place, and circular motion was the most perfect form of motion, eternal, unchanging, divine. The heavens rotated because rotation was their nature, he argued. Perfect celestial objects moved in perfect circles, and this had been true forever and would remain true forever. But there was a problem with the celestial sphere model, a problem that wouldn't become fully apparent until much later. If Earth was truly stationary and the entire cosmos was rotating around us once per day, then the stars, which were thought to be just beyond Saturn's orbit, would have to be moving at unimaginable speeds. Even in ancient times, some thinkers recognized this difficulty. The farther from Earth a star was, the faster it would have to move to complete a circle in 24 hours. If stars were very distant, they'd have to be racing through space at impossible velocities. This concern led a few ancient Greek astronomers, most notably Aristarchus of Samos around 270 BCE, to propose a radical alternative. Perhaps Earth itself was rotating, and the apparent motion of the heavens was simply an illusion caused by our own spinning. If Earth turned once per day on its axis, the sky would appear to wheel overhead even though the stars themselves were stationary. It was an elegant solution, a perfect example of what we now call the principle of relativity, that motion is relative, that you can't always tell who is moving and who is standing still. But Aristarchus's idea was rejected by nearly all his contemporaries. The objections seemed compelling, even obvious. If Earth were spinning, wouldn't we feel it? Wouldn't there be constant powerful winds as the atmosphere failed to keep up with the rotating ground? If you jumped straight up, wouldn't you land far to the west of where you started, since Earth would have rotated beneath you while you were in the air? Wouldn't birds flying eastward have an impossible struggle, flying against Earth's rotation, while birds flying westward would zip along effortlessly? None of these effects were observed, so Earth must be stationary. These objections would stand for nearly 2,000 years, a testament to how difficult it is to accept that we might be in motion when we feel perfectly still. The idea of a rotating Earth seemed to contradict common sense and everyday experience. How could we be spinning at enormous speeds and not feel it? How could the atmosphere, the oceans, loose objects on Earth's surface all be carried along perfectly with Earth's rotation? The ancients lacked the physics to answer these questions, lacked the concept of inertia that would eventually explain why everything on and near Earth's surface rotates along with the planet itself. It wasn't until the 16th century that the idea of Earth's rotation would be seriously revived, and even then it would take another century before it was widely accepted. Nicholas Copernicus, the Polish astronomer who in 1543 proposed that Earth and the other planets orbit the Sun, also argued that Earth rotates on its axis once per day. This rotation, Copernicus explained, was far simpler than imagining the entire vast cosmos spinning around tiny Earth. It made more sense that our small world turned while the universe remained still. But Copernicus couldn't prove Earth's rotation. He could argue it was more elegant, more logical, but he couldn't directly demonstrate it. The same objections that had defeated Aristarchus's proposal still applied. Where was the mighty wind that should result from rotation? Why didn't we feel the motion? Copernicus and his followers needed a new understanding of motion itself, a physics that could explain why objects on a rotating Earth would rotate along with it, feeling no wind, no lurch, no evidence of the tremendous speed at which they were actually moving. That new physics would come from Galileo Galilei in the early 1600s. Galileo thought deeply about motion and developed early concepts of what would later be called inertia, the principle that objects in motion tend to stay in motion, and objects at rest tend to stay at rest, unless acted upon by an external force. Galileo realized that if Earth had been rotating since its formation, everything on and near Earth, the atmosphere, the oceans, all objects on the surface, would have acquired that rotational motion. They would all be moving together, like passengers on a smoothly sailing ship. Just as you don't feel the motion of a ship moving at constant speed across calm water, you don't feel Earth's rotation because you're moving along with it. Galileo used the example of a ship to illustrate this principle. If you're below deck in a ship's cabin, moving at constant speed across smooth water, you can't tell by any experiment performed within the cabin whether the ship is moving or stationary. Drop a ball and it falls straight down. Toss it in the air and it comes straight back to your hand, even though the ship, and you, and the ball, are all moving forward. This is because you, the air in the cabin, and the ball are all moving together at the same velocity. The same principle applies to Earth's rotation. We, the atmosphere, and everything around us are all rotating together, so we perceive no motion. This insight was revolutionary. It meant that our common sense intuitions about motion were wrong, that we couldn't always trust our immediate perceptions. Just because we don't feel Earth rotating doesn't mean it isn't rotating. The absence of sensation isn't evidence of absence of motion, it's evidence that motion is relative, that what matters isn't absolute speed but relative speed. We don't feel Earth's rotation because there's no relative motion between us and our surroundings. Everything is turning together, in perfect synchronized motion. And so our journey has begun with the ancient observation that the heavens appear to rotate around Earth, the sun traveling from east to west, the stars wheeling overhead in great circles, all completing their motions in roughly 24 hours. This apparent celestial motion captivated every human culture, forming the basis for calendars and timekeeping, the rhythm around which life was organized. We learn the ancient Greeks developed sophisticated models to explain this rotation, imagining a great celestial sphere surrounding Earth with stars embedded in it like jewels, rotating once per day, carrying all celestial objects in their paths. Aristotle in 4th century BCE created an elaborate system of nested crystalline spheres rotating at different rates to explain sun, moon, and planet motions against fixed star background. Circular motion was most perfect form, eternal and divine, and the heavens rotated because rotation was their nature. We discovered a problem with the celestial sphere model. If Earth was truly stationary and entire cosmos rotating around us once per day, then stars would have to move at unimaginable speeds. The farther from Earth, the faster they'd have to move to complete their circle in 24 hours. This concern led some ancient Greek astronomers, notably Aristarchus of Samos around 270 BCE, to propose radical alternative. Perhaps Earth itself was rotating, and apparent heavenly motion was illusion caused by our own spinning. If Earth turned once per day on its axis, sky would appear to wheel overhead even though stars themselves stationary. We found Aristarchus's idea was rejected by nearly all contemporaries because objections seemed compelling. If Earth were spinning, wouldn't we feel it? Wouldn't there be constant powerful winds as atmosphere failed to keep up with rotating ground? If you jumped straight up, wouldn't you land far to west since Earth would have rotated beneath you while airborne? Wouldn't birds flying eastward struggle against Earth's rotation while birds flying westward zip along effortlessly? None of these effects observed, so Earth must be stationary. We learned these objections stood for nearly 2,000 years, testament to how difficult accepting we might be in motion when feeling perfectly still. Rotating Earth seemed to contradict common sense and everyday experience. How could we spin at enormous speeds and not feel it? How could atmosphere, oceans, loose objects all be carried along perfectly with Earth's rotation? Ancients lacked physics to answer these questions, lacked concept of inertia that would eventually explain why everything on and near Earth's surface rotates along with planet itself. We discovered 16th century idea of Earth's rotation seriously revived. Nicholas Copernicus, who in 1543 proposed Earth and other planets orbit Sun, also argued Earth rotates on axis once per day. This rotation, far simpler than imagining entire vast cosmos spinning around tiny Earth, made more sense that our small world turned while universe remained still. But Copernicus couldn't prove Earth's rotation, could argue it was more elegant, more logical, but couldn't directly demonstrate it. Same objections that defeated Aristarchus still applied. We met Galileo Galilei in early 1600s, who thought deeply about motion and developed early inertia concepts, principle that objects in motion tend to stay in motion, objects at rest tend to stay at rest, unless acted upon by external force. Galileo realized if Earth had been rotating since formation, everything on and near Earth, atmosphere, oceans, all surface objects, would have acquired that rotational motion, all moving together like passengers on smoothly sailing ship. Just as you don't feel ship's motion at constant speed across calm water, you don't feel Earth's rotation because you're moving along with it. We learned Galileo used ship example to illustrate principle. If you're below deck in ship's cabin moving at constant speed across smooth water, can't tell by any cabin experiment whether ship moving or stationary. Drop ball, it falls straight down. Toss, it returns straight to hand even though ship, you, and ball all moving forward, because you, cabin air, and ball all moving together at same velocity. Same principle applies to Earth's rotation. We, atmosphere, and everything around us all rotating together, so we perceive no motion. We discovered this insight was revolutionary, meant common sense motion intuitions were wrong, couldn't always trust immediate perceptions. Just because we don't feel Earth rotating doesn't mean it isn't rotating. Absence of sensation isn't evidence of absence of motion, it's evidence motion is relative. What matters isn't absolute speed but relative speed. We don't feel Earth's rotation because there's no relative motion between us and surroundings, everything turning together in perfect synchronized motion. Each fact a gentle step in understanding's awakening, the realization slowly dawning that the world beneath us is not still but turning, that we are all passengers on a spinning sphere, moving together so smoothly we perceive only stillness. The ancients watching the heavens turn, Aristarchus daring to suggest we are the ones spinning, Copernicus reviving the idea, Galileo explaining why we don't feel the motion, each mind building on the last, slowly assembling the truth. Feel yourself in that gentle understanding now, recognizing that even as you lie still, you are moving, turning with the Earth at 1,000 miles per hour, carried through space in a rotation so smooth and constant that it feels like perfect rest. There's nothing to solve tonight, nothing to grasp. Just rest in the slow turning of the world, in the peaceful rhythm of Earth's rotation, like a child rocked in a cradle, gentle and safe and still. Let the Earth carry you now, turning slowly beneath the stars, spinning through the darkness with you held safely on its surface, peaceful and unhurried, drifting gently towards sleep. As we continue our peaceful journey through the science of rotation, we move forward from Galileo's insight about relative motion into a time when scientists would begin to prove that Earth truly does rotate, and when they would start to understand the deeper question, not just that Earth spins, but why it spins, what causes rotation, and why it seems to be such a universal feature of everything in the cosmos. Galileo's explanation of why we don't feel Earth's rotation was intellectually satisfying, but it still wasn't proof. It explained away the objections to Earth's rotation, but it didn't provide direct evidence that rotation was actually happening. For that, scientists needed to find some observable effect of Earth's rotation, something that would be different if Earth were spinning versus if it were stationary. This search for evidence would occupy some of the finest scientific minds for the next few centuries. One of the first pieces of indirect evidence came from the study of winds and ocean currents. By the 18th century, sailors and navigators had noticed peculiar patterns in the way winds blow and currents flow. In the northern hemisphere, winds tend to curve to the right of their initial direction. In the southern hemisphere, they curve to the left. Weather systems, hurricanes and cyclones, spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. These patterns were consistent and global, hinting at some underlying cause related to Earth's structure or motion. In 1735, an English scientist named George Hadley proposed an explanation for these wind patterns that involved Earth's rotation. Hadley was trying to explain the trade winds, the steady winds that blow from east to west in the tropics, winds that sailors had relied upon for centuries to cross the oceans. Hadley reasoned that warm air rising at the equator would flow toward the poles at high altitude, then sink and flow back toward the equator at the surface. But, Hadley realized, if Earth were rotating, this simple circulation would be deflected. The key insight was this: Earth is a sphere, and different latitudes are moving at different speeds as Earth rotates. At the equator, Earth's surface is moving eastward at about 1,000 miles per hour. At higher latitudes, farther from the equator, the surface is moving more slowly. At 45 degrees latitude, the speed is about 700 miles per hour, and at the poles, the rotational speed is essentially zero. When air moves from the equator toward the poles, it carries with it the faster eastward motion of the equatorial regions. As it moves to higher latitudes where the ground is moving more slowly, the air finds itself moving faster eastward than the ground beneath it. From the perspective of someone on the rotating Earth, the air appears to curve to the right in the northern hemisphere. This deflection of moving objects caused by Earth's rotation would eventually be named the Coriolis effect, after the French scientist Gaspard Gustave de Coriolis, who described it mathematically in 1835. Coriolis showed that on a rotating sphere, any object moving across the surface, whether air, water, or even artillery shells, will appear to curve relative to the surface. The deflection is always to the right in the northern hemisphere and to the left in the southern hemisphere. The effect is stronger at higher latitudes and weaker near the equator, where it vanishes entirely. The Coriolis effect explains so many observed phenomena. It explained why hurricanes spin counterclockwise in the northern hemisphere. Air flowing inward toward the low-pressure center is deflected to the right, creating the characteristic rotation. It explained why ocean currents form great circular gyres, clockwise in the northern hemisphere and counterclockwise in the southern. It even had practical implications for long-range artillery during World War I, gunners had to account for the Coriolis deflection when aiming at distant targets, or their shells would miss by hundreds of feet. But the Coriolis effect, while powerful evidence for Earth's rotation, was still somewhat indirect. It required understanding complex fluid dynamics and accepting mathematical arguments about rotating reference frames. What scientists really wanted was a simple, direct demonstration that anyone could see, a smoking gun proof that Earth was rotating. That proof would come in 1851 from a French physicist named Léon Foucault, in one of the most elegant experiments in the history of science. Foucault's idea was beautifully simple. He suspended a heavy iron ball, about 60 pounds, from a long wire attached to the dome of the Pantheon in Paris. The wire was over 200 feet long, and the ball hung just above the floor. Foucault set this massive pendulum swinging in a straight line, back and forth, like any pendulum. The crucial insight was this: once set in motion, a pendulum will continue swinging in the same plane in space, according to Newton's laws of motion. The pendulum itself doesn't know about Earth's rotation, it just keeps swinging in the same direction relative to the fixed stars. But to observers standing on Earth's rotating surface, the pendulum's plane of oscillation appears to rotate slowly. At the Pantheon in Paris, which is at about 49 degrees north latitude, Foucault's pendulum appeared to rotate clockwise, completing a full circle in about 32 hours. This wasn't the pendulum rotating, it was the Earth rotating beneath the pendulum while the pendulum maintained its fixed orientation in space. Imagine watching a pendulum from a slowly rotating platform. The pendulum would appear to change direction even though it was actually swinging in a constant plane. That's exactly what Foucault demonstrated. The beauty of Foucault's pendulum was that it was direct, visual, undeniable. Thousands of people came to the Pantheon to watch the pendulum slowly shift its swing, to see with their own eyes the Earth rotating beneath them. Here was Earth's rotation made visible, transformed from an abstract concept into something you could witness in real time. Foucault pendulums were soon installed in buildings around the world, each one a patient demonstration of our planet's rotation. At the North or South Pole, a Foucault pendulum would complete a full apparent rotation in exactly 24 hours, one full day, as Earth turned beneath it. With Foucault's pendulum, the question of whether Earth rotates was finally settled beyond any reasonable doubt. Earth spins on its axis once every 23 hours and 56 minutes, not quite 24 hours, because we measure solar days by the sun's position, but Earth actually rotates slightly faster relative to the distant stars. This rotation has been constant and steady for billions of years, a fundamental characteristic of our planet. But why? Why does Earth rotate at all? What sent it spinning in the first place? The answer to this question would require understanding how Earth formed, and indeed how all planets and stars form. As astronomers in the 18th and 19th centuries studied the solar system, they noticed a striking pattern: all the planets orbit the Sun in the same direction. They all orbit in nearly the same plane, like runners on a cosmic racetrack. And most of them also rotate in the same direction as their orbits, counterclockwise if you're looking down on the solar system from above the Sun's North Pole. The Sun itself rotates in this same direction. The moons of planets generally orbit in the same direction as their planet's rotation. This wasn't coincidence. Such a systematic pattern suggested a common origin, a shared history. The nebular hypothesis, first proposed by Immanuel Kant in 1755 and later developed by Pierre-Simon Laplace, provided the explanation. According to this theory, the solar system formed from a vast rotating cloud of gas and dust, a nebula. This cloud was slowly rotating initially, perhaps set in motion by the gravitational influences of nearby stars, or by turbulent motions in the larger galactic cloud from which it condensed. As this rotating nebula contracted under its own gravity, it spun faster. This is a consequence of the law of conservation of angular momentum, one of the most fundamental principles in physics. Angular momentum is a measure of rotational motion. It depends on how fast something is spinning and how spread out its mass is. The law states that in a closed system, angular momentum cannot be created or destroyed, only redistributed. When a rotating cloud of gas contracts, pulling its mass closer to the center, it must spin faster to conserve angular momentum. You can see this principle in action when ice skaters spin. When a skater pulls her arms in close to her body, she spins faster. When she extends her arms, she spins more slowly. Her angular momentum stays constant, but by changing how spread out her mass is, she changes her rotation rate. The same thing happened to the solar nebula. As it contracted, it spun faster and faster, eventually flattening into a disc shape, much like how pizza dough flattens and spreads when you spin it. And so we moved beyond Galileo's explanation of why we don't feel Earth's rotation into the search for direct evidence that rotation was actually happening. While Galileo explained away objections, scientists needed observable effects of Earth's rotation, something different if Earth's spinning versus stationary. This search would occupy finest scientific minds for next few centuries. We discovered first indirect evidence came from studying winds and ocean currents. By 18th century sailors and navigators noticed peculiar patterns. Northern hemisphere winds tend to curve right of initial direction, southern hemisphere curve left. Weather systems, hurricanes, cyclones, spin counterclockwise in northern hemisphere, clockwise in southern. These patterns consistent and global, hinting at underlying cause related to Earth's structure or motion. We met George Hadley, who in 1735 proposed explanation for wind patterns involving Earth's rotation, trying to explain trade winds, steady east-to-west tropical winds sailors relied upon for centuries to cross oceans. Hadley reasoned warm equatorial air rising would flow toward poles at high altitude, then sink and flow back toward equator at surface, but if Earth rotating, this simple circulation would be deflected. We learned the key insight: Earth is sphere, different latitudes moving at different speeds as Earth rotates, equator surface moving eastward about 1,000 miles per hour, at higher latitudes, farther from equator, surface moving more slowly, 45 degrees latitude about 700 miles per hour, at poles essentially zero. When air moves from equator toward poles, carries with it faster eastward motion of equatorial regions, moving to higher latitudes where ground moving more slowly, air finds itself moving faster eastward than ground beneath it. From perspective of someone on rotating Earth, air appears to curve to right in northern hemisphere. We discovered this deflection of moving objects caused by Earth's rotation, eventually named Coriolis effect after French scientist Gaspard Gustave de Coriolis, who described it mathematically in 1835. Coriolis showed on rotating sphere any object moving across surface, air, water, even artillery shells, will appear to curve relative to surface, deflection always to right in northern hemisphere, to left in southern, effect stronger at higher latitudes, weaker near equator where it vanishes entirely. We found Coriolis effect explained many observed phenomena: why hurricanes spin counterclockwise in northern hemisphere, air flowing inward toward low-pressure center deflected to right creating characteristic rotation, why ocean currents form great circular gyres, clockwise in northern hemisphere, counterclockwise in southern, even had practical World War I implications. Long-range artillery gunners had to account for Coriolis deflection when aiming at distant targets or shells would miss by hundreds of feet. We learned Coriolis effect while powerful evidence for Earth's rotation was still somewhat indirect, required understanding complex fluid dynamics and accepting mathematical arguments about rotating reference frames. What scientists really wanted was simple direct demonstration anyone could see: smoking gun-proof Earth was rotating. That proof came 1851 from French physicist Léon Foucault in one of history's most elegant experiments. We discovered Foucault's beautifully simple idea: suspended heavy iron ball, about 60 pounds, from long wire attached to Pantheon Dome in Paris, wire over 200 feet long, ball hung just above floor. Foucault set this massive pendulum swinging in straight line back and forth like any pendulum. Crucial insight: once set in motion, pendulum will continue swinging in same plane and space according to Newton's motion laws. Pendulum itself doesn't know about Earth's rotation, just keeps swinging in same direction relative to fixed stars. We found to observers standing on Earth's rotating surface, pendulum's oscillation plane appears to rotate slowly. At Pantheon in Paris, about 49 degrees north latitude, Foucault's pendulum appeared to rotate clockwise, completing full circle in about 32 hours. Wasn't pendulum rotating but Earth rotating beneath pendulum while pendulum maintained fixed space orientation. Imagine watching pendulum from slowly rotating platform. Pendulum would appear to change direction even though actually swinging in constant plane. We learned Foucault's pendulum beauty was that it was direct, visual, undeniable. Thousands came to Pantheon to watch pendulum slowly shift its swing, see with own eyes Earth rotating beneath them. Earth's rotation made visible, transformed from abstract concept into something witnessable in real time. Foucault pendulums soon installed in buildings worldwide, each one patient demonstration of our planet's rotation. At North or South Pole, Foucault pendulum would complete full apparent rotation in exactly 24 hours, one full day, as Earth turned beneath it. We discovered with Foucault's pendulum, question of whether Earth rotates finally settled beyond reasonable doubt. Earth spins on axis once every 23 hours and 56 minutes. Not quite 24 hours because we measure solar days by sun's position, but Earth actually rotates slightly faster relative to distant stars. This rotation constant and steady for billions of years, fundamental planetary characteristic. But why? Why does Earth rotate at all? What set it spinning in first place? We found answering this question required understanding how Earth formed, indeed how all planets and stars form. As 18th and 19th century astronomers studied solar system, noticed striking pattern: all planets orbit Sun in same direction, all orbit in nearly same plane like runners on cosmic racetrack, and most also rotate in same direction as their orbits, counterclockwise if looking down on solar system from above Sun's north pole. Sun itself rotates this same direction. Planet moons generally orbit in same direction as their planet's rotation. We learned this wasn't coincidence. Such systematic patterns suggested common origin, shared history. Nebular hypothesis, first proposed by Immanuel Kant 1755 and later developed by Pierre-Simon Laplace, provided explanation. Solar system formed from vast rotating gas and dust cloud. Nebula. Cloud was slowly rotating initially, perhaps set in motion by nearby star gravitational influences or by turbulent motions in larger galactic cloud from which it condensed. We discovered as this rotating nebula contracted under own gravity, spun faster, consequence of conservation of angular momentum law, one of physics' most fundamental principles. Angular momentum is rotational motion measure, depends on how fast something's spinning and how spread out its mass is. Law states in closed system angular momentum cannot be created or destroyed, only redistributed. When rotating gas cloud contracts, pulling mass closer to center, must spin faster to conserve angular momentum. We found this principle in action when ice skaters spin. When skater pulls arms and close to body spins faster, when extends arms spins more slowly, angular momentum stays constant, but by changing how spread out mass is, changes rotation rate. Same thing happened to solar nebula. As it contracted, spun faster and faster, eventually flattening into disk shape, much like how pizza dough flattens and spreads when you spin it. Each fact a gentle step in understanding's deepening, the gradual realization that Earth's rotation isn't arbitrary but has a cause, a history written in the formation of our solar system. The Coriolis effect, curving winds and waters, Foucault's pendulum making rotation visible, the nebular hypothesis explaining why everything in our solar system spins in the same direction, all pieces of one beautiful story. Rest in this understanding now, this recognition that the turning beneath you has been happening for 4.5 billion years, that it began when our solar system was just a cloud of dust and gas slowly contracting and spinning faster. You are carried by rotation older than mountains, older than oceans, older than life itself, steady and eternal and gentle. Let yourself drift with Earth's ancient spin, turning slowly through space, peaceful and unhurried, carried gently toward sleep. As we continue our peaceful journey through the science of rotation, we move from understanding why Earth spins to exploring the deeper implications of that rotation, and how the principle of angular momentum, this beautiful law of conservation, governs not just our planet but every spinning object in the universe, from the smallest atoms to the largest galaxies. The solar nebula that formed our solar system didn't just collapse uniformly inward. As it spun faster and faster due to conservation of angular momentum, the rotation itself began to shape how it collapsed. Think about what happens when you spin something. Centrifugal effects push material outward, away from the axis of rotation. This is why figure skaters extend their arms to slow down, and why you feel pushed outward when you ride on a spinning carnival ride. The same principle affected the collapsing nebula. Material falling toward the center could move easily along the axis of rotation, perpendicular to the disk, but material trying to fall in from the sides was held back by its own rotation. The result was that the nebula flattened into a disk, thicker at the center where the protosun was forming, and thinner toward the edges where the planets would eventually form. This is why the solar system is flat, why all the planets orbit in nearly the same plane. They formed from this rotating disk, and they inherited its geometry, its orientation, its direction of spin. Within this disk, dust particles collided and stuck together, gradually building up larger bodies through a process called accretion. Small grains became pebbles, pebbles became boulders, boulders became planetesimals miles across. These planetesimals, as they grew through countless collisions with smaller objects, began to spin. Each collision imparted angular momentum, and because collisions came from random directions, each planetesimal acquired a net rotation. Most of these growing worlds ended up rotating in the same general direction as the disk itself was rotating, the same direction we see today in the planet's orbits and spins. But the collisions that built the planets were not always gentle or small. As planetesimals grew larger, their gravity grew stronger, allowing them to capture more and more material. Sometimes, massive collisions occurred, encounters between bodies hundreds or thousands of miles across, impacts releasing energy equivalent to billions of nuclear bombs. These giant impacts could dramatically affect a planet's rotation. A glancing blow from a large object could speed up a planet's rotation, or slow it down, or even knock it over, changing the tilt of its rotational axis. We see evidence of such violent collisions throughout the solar system. Venus rotates very slowly and backward compared to most planets. It takes 243 Earth days to complete one rotation, and it spins in the opposite direction from its orbit around the Sun. This retrograde rotation was likely caused by one or more massive impacts early in Venus's history that either reversed its original rotation or slowed it down so much that tidal forces from the Sun reversed it over time. Venus turns so slowly that its day is actually longer than its year. It takes less time to orbit the Sun than to complete one rotation on its axis. Uranus provides an even more dramatic example. As we learned earlier, Uranus rotates on its side, with its axis tilted about 98 degrees. Instead of spinning like a top as it orbits the Sun, Uranus rolls like a ball, with its poles pointing nearly directly at the Sun during different parts of its orbit. The only plausible explanation for this extreme tilt is a massive collision with an Earth-sized object during the late stages of planetary formation. Such an impact would have delivered an enormous amount of angular momentum at just the right angle to tip Uranus over onto its side, where it has remained for billions of years. Our own Earth's rotation also bears the mark of a giant impact. The leading theory for the Moon's formation, called the giant impact hypothesis, proposes that about 4.5 billion years ago, when Earth was still young and molten, it was struck by a Mars-sized object that scientists have named Theia. This collision was catastrophic. The impact vaporized much of Theia and tore away a large portion of Earth's outer layers. The debris from this impact went into orbit around Earth and eventually coalesced to form the Moon. This giant impact had profound effects on Earth's rotation. Before the collision, Earth was probably already rotating, but the impact from Theia added angular momentum, potentially causing Earth to spin much faster than it does today. Some models suggest that immediately after the giant impact, Earth's day might have been only 5 or 6 hours long. The planet was spinning so rapidly that it was noticeably flattened at the poles and bulged at the equator. Over billions of years, Earth's rotation has gradually slowed down due to tidal interactions with the Moon, which we'll explore more in a moment. The Moon that formed from the debris of the giant impact also inherited rotation, but in a peculiar way. The Moon rotates on its axis at exactly the same rate that it orbits Earth. It takes about 27.3 days to complete one rotation, and exactly the same time to complete one orbit. This perfect synchronization means that the Moon always shows the same face to Earth. We never see the far side of the moon from Earth, not because it's dark, it receives just as much sunlight as the near side, but because the moon's rotation is locked to its orbit. This phenomenon is called tidal locking, and it's the result of tidal forces between Earth and the moon. Tidal forces are differences in gravitational pull across an extended object. Earth's gravity pulls more strongly on the side of the moon facing Earth than on the far side. This difference creates a slight bulge in the moon. The moon is very subtly elongated, stretched toward Earth. When the moon was younger and rotating faster, this bulge tried to rotate along with the moon, but Earth's gravity pulled on the bulge, creating a torque that slowed the moon's rotation. Over millions of years, this tidal torque gradually slowed the moon's rotation until it reached the current state where the rotation period matches the orbital period perfectly. At this point, the tidal bulge always faces Earth. There's no more relative motion to create torque, and the moon remains locked with one face always toward Earth. This tidal locking is not unique to our moon. It's extremely common in the solar system. Most large moons in the solar system are tidally locked to their parent planets. Io, Europa, Ganymede, and Callisto are all locked to Jupiter. Titan is locked to Saturn. Even Pluto and Charon are mutually tidally locked, always showing the same face to each other as they orbit their common center of gravity. But tidal forces don't just affect moons, they also affect planets. The moon exerts tidal forces on Earth, creating the ocean tides we see every day. The moon's gravity pulls water on the side of Earth facing the moon, creating a bulge of high water. There's also a corresponding bulge on the opposite side of Earth, created by the fact that the moon pulls the solid Earth more than it pulls the water on the far side. As Earth rotates beneath these tidal bulges, we experience high tides when we rotate into a bulge and low tides when we're between the bulges. But here's the crucial point for understanding rotation. Earth rotates faster than the moon orbits. Earth completes a rotation in 24 hours, while the moon takes about 27.3 days to orbit. This means that Earth's rotation carries the tidal bulges slightly ahead of the line connecting Earth and Moon. The bulge isn't directly under the moon, but slightly ahead of it. The moon's gravity pulls back on this bulge, creating a torque that gradually slows Earth's rotation. The same effect that tidally locked the moon to Earth is now gradually slowing Earth's rotation. The effect is small but measurable. Earth's rotation is slowing down by about 1.7 milliseconds per century. This means that days are very gradually getting longer. When dinosaurs walked the Earth, a day was perhaps 23 hours long. When Earth first formed, days might have been only 5 or 6 hours. Billions of years in the future, if Earth and the Moon survive that long, Earth will eventually become tidally locked to the Moon, with both bodies showing the same face to each other, rotating and orbiting in perfect synchronization, each day equal to about 47 of our current days. And so we learned the solar nebula didn't just collapse uniformly inward. As it spun faster due to angular momentum conservation, rotation itself began to shape collapse. Centrifugal effects push material outward away from rotation axis, like figure skaters extending arms to slow down, or feeling pushed outward on spinning carnival ride. Material falling towards center could move easily along rotation axis, perpendicular to disk, but material from sides was held back by own rotation. Result was nebula flattened into disk, thicker at center, protosun forming, thinner toward edges, planets would form. This is why solar system is flat, why all planets orbit a nearly same plane, formed from rotating disk, inherited its geometry, orientation, spin direction. We discovered within this disk, dust particles collided and stuck together, gradually building larger bodies through accretion. Small grains became pebbles, pebbles became boulders, boulders became miles across planetesimals. As planetesimals grew through countless smaller object collisions, began to spin, each collision imparted angular momentum. Because collisions came from random directions, each planetesimal acquired net rotation. Most growing worlds ended up rotating in same general direction as disk itself was rotating, same direction we see today in planets' orbits and spins. We found collisions building planets were not always gentle or small. As planetesimals grew larger, gravity grew stronger, allowing them to capture more material. Sometimes massive collisions occurred, encounters between bodies hundreds or thousands of miles across, impacts releasing energy equivalent to billions of nuclear bombs. These giant impacts could dramatically affect planets' rotation. Glancing blow from large object could speed up rotation, slow it down, or even knock it over, changing rotational axis tilt. We learned we see evidence of violent collisions throughout solar system. Venus rotates very slowly and backward compared to most planets, takes 243 Earth days to complete one rotation, spins in opposite direction from its Sun orbit. This retrograde rotation likely caused by one or more massive early history impacts that either reversed original rotation or slowed it down so much that Sun tidal forces reversed it over time. Venus turns so slowly its day is actually longer than its year, takes less time to orbit Sun than to complete one axis rotation. We discovered Uranus provides even more dramatic example. Rotates on its side with axis tilted about 98 degrees. Instead of spinning like top as it orbits Sun, Uranus rolls like ball with poles pointing nearly directly at Sun during different orbit parts. Only plausible explanation for extreme tilt is massive collision with Earth-sized object during late planetary formation stages. Such impact would have delivered enormous angular momentum at just right angle to tip Uranus over onto its side, where it has remained for billions of years. We found our own Earth's rotation also bears giant impact mark. Leading moon formation theory, giant impact hypothesis, proposes about 4.5 billion years ago when Earth's still young and molten, it was struck by Mars-sized object. Scientists named Theia. Catastrophic collision vaporized much of Theia and tore away large Earth outer layer portion. Impact debris went into Earth orbit, eventually coalesced to form Moon. We learned giant impact had profound effects on Earth's rotation. Before collision Earth probably already rotating, but Theia impact added angular momentum, potentially causing Earth to spin much faster than today. Some models suggest immediately after giant impact, Earth's day might have been only 5 or 6 hours long, planet spinning so rapidly it was noticeably pole flattened and equator bulged. Over billions of years Earth's rotation has gradually slowed down due to tidal moon interactions. We discovered Moon formed from giant impact debris also inherited rotation, but in peculiar way. Moon rotates on axis at exactly same rate it orbits Earth, takes about 27.3 days to complete one rotation, exactly same time to complete one orbit. This perfect synchronization means Moon always shows same face to Earth. We never see Moon's far side, not because it's dark, receives just as much sunlight as near side, but because Moon's rotation is locked to its orbit. We found this phenomenon called tidal locking results from tidal forces between Earth and Moon. Tidal forces are gravitational pull differences across extended object. Earth's gravity pulls more strongly on Moon's side facing Earth than on far side, creating slight moon bulge, Moon very subtly elongated, stretched toward Earth. When Moon was younger and rotating faster, this bulge tried to rotate along with Moon, but Earth's gravity pulled on bulge, creating torque that slowed Moon's rotation. We learned over millions of years this tidal torque gradually slowed Moon's rotation until reaching current state where rotation period matches orbital period perfectly. Tidal bulge always faces Earth. No more relative motion to create torque. Moon remains locked with one face always toward Earth. Tidal locking not unique to our Moon, extremely common in solar system. Most large solar system moons are tidally locked to parent planets, Io, Europa, Ganymede, Callisto all locked to Jupiter, Titan locked to Saturn, even Pluto and Charon mutually tidally locked, always showing same face to each other. We discovered tidal forces don't just affect moons but also planets. Moon exerts tidal forces on Earth, creating ocean tides we see daily. Moon's gravity pulls water on Earth's side facing Moon, creating high water bulge, also corresponding bulge on opposite Earth's side. Moon pulls solid Earth more than water on far side. As Earth rotates beneath these tidal bulges, we experience high tides rotating into bulge, low tides between bulges. We found crucial rotation point. Earth rotates faster than Moon orbits. Earth completes rotation in 24 hours while Moon takes about 27.3 days to orbit. Means Earth's rotation carries tidal bulges slightly ahead of Earth-Moon connecting line. Bulge isn't directly under Moon but slightly ahead of it. Moon's gravity pulls back on this bulge, creating torque that gradually slows Earth's rotation. Same effect that tidally locked Moon to Earth, now gradually slowing Earth's rotation. We learned effect is small but measurable. Earth's rotation slowing by about 1.7 milliseconds per century. Days very gradually getting longer. When dinosaurs walked Earth, day was perhaps 23 hours long. When Earth first formed, days might have been only 5 or 6 hours. Billions of years in future, if Earth and Moon survive that long, Earth will eventually become tidally locked to Moon with both bodies showing same face to each other, rotating and orbiting in perfect synchronization, each day equal to about 47 of our current days. Each fact a gentle step in understanding's deepening, the realization that rotation is not static but dynamic, constantly changing through the slow patient work of tidal forces. The Moon locked to Earth, Earth gradually slowing, Venus turning backward from ancient collisions, Uranus rolling on its side, each world bearing the marks of its violent history, each carrying the angular momentum imparted by ancient impacts billions of years ago. Rest in this patient transformation now, this recognition that even rotation changes, that the spin you feel is slower than yesterday's spin, that eons from now Earth will turn even more slowly, the Moon will drift farther, the days will stretch longer. But for tonight, the rotation is steady, constant, carrying you peacefully through space. Let yourself drift with this ancient, slowing spin, turning gently through the darkness, peaceful and unhurried, carried softly towards sleep. As we continue our peaceful journey through the science of rotation, we move beyond our own Earth and Moon to explore how rotation affects all celestial bodies, and how this universal spinning motion reveals itself in ways both subtle and spectacular, from the shape of planets to the structure of entire galaxies spinning through the cosmos. The rotation of planets doesn't just affect when the sun rises and sets, it actually changes the physical shape of the planets themselves. A perfectly stationary sphere would be round in all directions, but a rotating sphere experiences centrifugal effects that cause it to bulge at the equator and flatten at the poles. The faster an object rotates, the more pronounced this effect becomes. You can see this principle in action with something as simple as pizza dough. When you spin the dough, it flattens and spreads outward, becoming wider at the edges. Earth itself is not a perfect sphere but an oblate spheroid. It's slightly flattened at the poles and bulges at the equator. The difference is small but measurable. Earth's equatorial diameter is about 7,926 miles, while the pole-to-pole diameter is about 7,900 miles, a difference of roughly 26 miles. This means that standing at the equator, you are about 13 miles farther from Earth's center than you would be standing at the North or South Pole. This bulge exists entirely because of Earth's rotation. If Earth suddenly stopped spinning, over thousands of years the planet would gradually relax into a more perfect sphere as the equatorial bulge slowly redistributed toward the poles. Other planets show even more dramatic rotational flattening because they spin faster than Earth. Jupiter, the largest planet in our solar system, rotates incredibly rapidly. It completes one full rotation in just under 10 hours, despite being more than 11 times wider than Earth. This rapid rotation causes Jupiter to be noticeably flattened. Jupiter's equatorial diameter is about 88,846 miles, while its polar diameter is only about 83,082 miles, a difference of nearly 6,000 miles, or about 7%. Even through a small telescope, you can see that Jupiter appears wider than it is tall, a visual testament to the power of rotation to reshape an entire world. Saturn shows an even more extreme example. Saturn rotates in just over 10.5 hours and is much less dense than Jupiter. It's composed largely of hydrogen and helium, making it light enough that it would actually float in water if you could find an ocean large enough. This combination of rapid rotation and low density causes Saturn to be the most flattened planet in the solar system. Saturn's equatorial diameter is about 74,898 miles, while its polar diameter is only about 67,560 miles, a difference of more than 7,300 miles, or about 10%. Through a telescope, Saturn appears distinctly oval, its rotational bulge clearly visible even to amateur observers. But rotation doesn't just affect the shape of planets, it also affects their internal structure and their magnetic fields. Deep inside Earth, there is a liquid outer core made primarily of molten iron and nickel. As Earth rotates, this liquid metal flows and swirls in complex patterns. These flowing motions of electrically conductive liquid metal generate electric currents, and these currents in turn create Earth's magnetic field through a process called the geodynamo. It's essentially a natural dynamo, converting the rotational energy of the planet into a magnetic field that extends far out into space. Earth's magnetic field is crucial for life as we know it. The field extends tens of thousands of miles into space, creating a protective bubble called the magnetosphere that deflects most of the solar wind, the constant stream of charged particles flowing from the sun. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as appears to have happened to Mars, which lost its magnetic field billions of years ago when its core cooled and solidified. The fact that Earth still has a strong magnetic field is directly related to its rotation and its still molten outer core. Other planets with liquid interiors and relatively rapid rotation also generate magnetic fields through the same dynamo process. Jupiter has an incredibly powerful magnetic field, far stronger than Earth's, generated by the motion of metallic hydrogen deep within its interior as the planet rapidly rotates. Saturn, Uranus, and Neptune also have substantial magnetic fields. But Venus, which rotates so slowly that its day is longer than its year, has virtually no magnetic field at all. Mars, which rotates at a similar rate to Earth but has a solid core, also lacks a global magnetic field. Rotation is essential. Without it, there's no motion of conductive fluids, no dynamo, no magnetic field. The Sun itself rotates, and its rotation is visible in the movement of sunspots across its surface. Galileo was one of the first to observe this, noting that dark spots on the Sun's face moved from day to day, appearing on one edge of the solar disk, traveling across, and disappearing on the opposite edge about 2 weeks later, evidence that the Sun was rotating. But the Sun's rotation is peculiar. Unlike solid bodies like Earth, which rotate as unified objects, the Sun is made entirely of gas and plasma, and different parts of it rotate at different rates. This phenomenon is called differential rotation. The Sun's equator rotates faster than its poles. The equatorial regions complete one rotation in about 25 days, while the polar regions take about 35 days. This differential rotation is possible because the Sun has no solid surface to enforce uniform rotation. The result is that the Sun's magnetic field, which is generated by motions in its electrically conductive plasma, becomes twisted and tangled over time. These tangled magnetic field lines emerge from the Sun's surface as sunspots, regions where strong magnetic fields suppress the normal convection of hot gas, creating cooler, darker patches on the solar surface. The Sun's differential rotation and the complex magnetic fields it generates are responsible for the solar cycle, the approximately 11-year period during which sunspot activity waxes and wanes. At solar maximum, the Sun is covered with many sunspot groups, and solar activity is high with frequent solar flares and coronal mass ejections. At solar minimum, the Sun may go weeks with no visible sunspots at all. This cycle is directly driven by the Sun's rotation and the way it winds up and reconfigures its magnetic field. After about 11 years, the magnetic field becomes so twisted that it flips, the Sun's north and south magnetic poles reverse, and then the cycle begins again. The rotation of the Sun had another profound consequence for the formation of the solar system, one that helped solve a mystery we mentioned earlier. Remember the angular momentum problem, the puzzle of why the Sun rotates relatively slowly despite containing most of the solar system's mass? The Sun contains about 99.86% of the solar system's total mass, but it contains only about 2% of the total angular momentum. The planets, despite their small mass, carry about 98% of the angular momentum in their orbital motion. Why? The answer lies in the interaction between the young Sun's rotation and its magnetic field. When the Sun was forming from the collapsing solar nebula, it was rotating much faster than it does today. But the Sun's magnetic field extended outward through the surrounding disk of gas and dust from which the planets would form. This magnetic field coupled the Sun to the disk, creating a magnetic break. As the disk orbited the Sun, The magnetic field transmitted torque from the rapidly spinning sun to the more slowly orbiting disk material, gradually slowing the sun's rotation while speeding up the orbital motion of material in the disk. Over millions of years, this magnetic braking transferred angular momentum from the sun to the disk, explaining why the sun rotates so slowly today while the planets carry most of the angular momentum. The young sun also experienced another form of braking through its solar wind, a powerful outflow of charged particles that carried angular momentum away from the sun together. These processes allowed the sun to shed much of its initial angular momentum, solving the puzzle of the distribution of spin in the solar system. And so we learned rotation of planets doesn't just affect when sun rises and sets but actually changes physical planet shapes. Perfectly stationary sphere would be round in all directions, but rotating sphere experiences centrifugal effects causing equatorial bulge and polar flattening, faster rotation, more pronounced effect, like spinning pizza dough flattens and spreads outward becoming wider at edges. We discovered Earth itself is not perfect sphere but oblate spheroid, slightly pole-flattened and equator-bulged. Difference small but measurable. Earth's equatorial diameter about 7,926 miles while pole-to-pole diameter about 7,900 miles. Difference roughly 26 miles. Standing at equator you are about 13 miles farther from Earth's center than at North or South Pole. This bulge exists entirely because of Earth's rotation. If Earth suddenly stopped spinning, over thousands of years planet would gradually relax into more perfect sphere as equatorial bulge slowly redistributed toward poles. We found other planets show more dramatic rotational flattening because spin faster than Earth. Jupiter, largest solar system planet, rotates incredibly rapidly, completes one full rotation in just under 10 hours despite being more than 11 times wider than Earth. This rapid rotation causes Jupiter to be noticeably flattened. Equatorial diameter about 88,846 miles while polar diameter only about 83,082 miles. Difference nearly 6,000 miles or about 7%. Even through small telescope Jupiter appears wider than tall, visual testament to rotation's power to reshape entire world. We learned Saturn shows even more extreme example. Rotates in just over 10.5 hours, much less dense than Jupiter, composed largely of hydrogen and helium, light enough to float in water if could find large enough ocean. This combination of rapid rotation and low density causes Saturn to be solar system's most flattened planet. Equatorial diameter about 74,898 miles while polar diameter only about 67,560 miles. Difference more than 7,300 miles or about 10%. Through telescope Saturn appears distinctly oval. Rotational bulge clearly visible even to amateur observers. We discovered rotation doesn't just affect planet shape but also internal structure and magnetic fields. Deep inside Earth is liquid outer core made primarily of molten iron and nickel. As Earth rotates, this liquid metal flows and swirls in complex patterns. These flowing motions of electrically conductive liquid metal generate electric currents. Currents in turn create Earth's magnetic field through process called geodynamo, essentially natural dynamo converting planetary rotational energy into magnetic field extending far into space. We found Earth's magnetic field crucial for life as we know it. Field extends tens of thousands of miles into space creating protective magnetosphere bubble that deflects most solar wind. Constant charged particle stream from sun. Without this magnetic shield, solar wind would gradually strip away Earth's atmosphere, as appears to have happened to Mars, which lost magnetic field billions of years ago when core cooled and solidified. Fact that Earth still has strong magnetic field directly related to its rotation and still molten outer core. We learned other planets with liquid interiors and relatively rapid rotation also generate magnetic fields through same dynamo process. Jupiter has incredibly powerful magnetic field, far stronger than Earth's, generated by metallic hydrogen motion deep within interior as planet rapidly rotates. Saturn, Uranus, Neptune also have substantial magnetic fields. But Venus, rotating so slowly its day longer than year, has virtually no magnetic field. Mars, rotating at similar Earth rate but with solid core, also lacks global magnetic field. Rotation is essential. Without it, no conductive fluid motion, no dynamo, no magnetic field. We discovered Sun itself rotates. Rotation visible in sunspot movement across surface. Galileo among first to observe this, noting dark sun face spots moved day to day, appearing on one solar disk edge, traveling across, disappearing on opposite edge about 2 weeks later, evidence Sun rotating. But Sun's rotation peculiar, unlike solid bodies like Earth rotating as unified objects. Sun made entirely of gas and plasma, different parts rotate at different rates. We found this phenomenon called differential rotation. Sun's equator rotates faster than poles. Equatorial regions complete one rotation in about 25 days while polar regions take about 35 days. Differential rotation possible because Sun has no solid surface to enforce uniform rotation. Result is Sun's magnetic field, generated by motions in electrically conductive plasma, becomes twisted and tangled over time. Tangled magnetic field lines emerge from Sun's surface as sunspots, regions where strong magnetic fields suppress normal hot gas convection, creating cooler, darker patches on solar surface. We learned Sun's differential rotation and complex magnetic fields it generates are responsible for solar cycle, approximately 11-year period during which sunspot activity waxes and wanes. At solar maximum, Sun covered with many sunspot groups, high solar activity with frequent solar flares and coronal mass ejections. At solar minimum, Sun may go weeks with no visible sunspots. This cycle directly driven by Sun's rotation and way it winds up and reconfigures magnetic field. After about 11 years, magnetic field becomes so twisted it flips. Sun's north and south magnetic poles reverse, then cycle begins again. We discovered Sun's rotation had another profound solar system formation consequence, helping solve angular momentum mystery mentioned earlier. Sun contains about 99.86% of solar system's total mass but only about 2% of total angular momentum. Planets, despite small mass, carry about 98% of angular momentum in their orbital motion. Why? Answer lies in interaction between young Sun's rotation and its magnetic field. We found when Sun was forming from collapsing solar nebula, was rotating much faster than today. But Sun's magnetic field extended outward through surrounding gas and dust disk, from which planets would form. Magnetic field coupled Sun to disk, creating magnetic brake. As disk orbited Sun, magnetic field transmitted torque from rapidly spinning Sun to more slowly orbiting disk material, gradually slowing Sun's rotation while speeding up disk material orbital motion. We learned over millions of years this magnetic braking transferred angular momentum from Sun to disk. explaining why Sun rotates so slowly today while planets carry most angular momentum. Young Sun also experienced another breaking form through solar wind, powerful charged particle outflow carrying angular momentum away from Sunday. Together these processes allowed Sun to shed much initial angular momentum, solving solar system spin distribution puzzle. Each fact a gentle reminder of rotation's pervasive effects, how spinning shapes worlds into oblate spheroids, how it generates protective magnetic fields, how differential rotation in the Sun creates the solar cycle's rhythm. Everything affected by spin, planets flattened, magnetic fields generated, angular momentum redistributed through magnetic braking across millions of years. Rest in this understanding now, this recognition that rotation is not just motion but force, reshaping, generating, protecting. The bulge at Earth's equator, the magnetic field shielding you from solar wind, the slowly turning Sun with its spots migrating across its face, all consequences of rotation, all part of the spinning universe. Let yourself drift with these turning forces, these ancient rotations reshaping worlds and generating fields, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the science of rotation, we move outward from our solar system to explore how rotation governs not just planets and stars, but entire galaxies, vast cosmic islands containing hundreds of billions of stars, all spinning together in a majestic dance that takes hundreds of millions of years to complete. Our own galaxy, the Milky Way, is a giant spiral galaxy containing somewhere between 200 and 400 billion stars, along with vast clouds of gas and dust, all bound together by gravity and all rotating around a common center. When you look up at the night sky and see that misty band of light stretching across the heavens, the band that gave our galaxy its name, you're looking edge-on through the disk of our galaxy, seeing the combined light of billions of distant stars all spinning together in the galactic rotation. The Milky Way rotates, but not like a solid disk or a spinning wheel. Like the Sun with its differential rotation, different parts of the galaxy rotate at different speeds. However, the pattern is surprising and reveals something profound about the nature of galaxies. Based on the visible matter, the stars and glowing gas clouds we can see, astronomers expected that regions farther from the galactic center would rotate more slowly, just as outer planets in our solar system orbit more slowly than inner planets. This is what Newton's laws predict. The farther you are from a gravitating mass, the weaker its pull, and the slower your orbital motion should be. But when astronomers measured the actual rotation speeds of stars and gas clouds at different distances from the galactic center, they found something unexpected. Instead of slowing down with distance, the rotation speed remained roughly constant out to the visible edge of the galaxy and perhaps beyond. Stars in the outer regions of the galaxy were moving much faster than they should be based on the visible matter. This flat rotation curve, as it's called, was one of the first clear pieces of evidence for dark matter, mysterious invisible matter that doesn't emit or absorb light but exerts gravitational influence. The astronomer Vera Rubin, working in the 1970s, was instrumental in establishing this result through careful observations of galaxy rotation curves. What she and others found was that galaxies must be embedded in enormous halos of dark matter, extending far beyond the visible disk. This dark matter provides the additional gravitational pull needed to keep the outer stars moving as fast as they do. Without dark matter, galaxies would rotate differently, and outer stars would actually be flung away into space, Their rotation speeds are too high for the visible matter alone to hold them in orbit. The fact that galaxies hold together despite their fast rotation tells us that most of a galaxy's mass is invisible to us, detectable only through its gravitational effects. This discovery transformed our understanding of the universe. It means that the stars, gas, and dust we can see, everything telescopes can detect, represents only about 15% of the total matter in galaxies. The other 85% is dark matter, matter that doesn't interact with light at all. We still don't know what dark matter is made of, despite decades of searching. It's one of the greatest mysteries in modern physics. But its existence is revealed through rotation, through the way galaxies spin. Rotation tells us that there's far more to the universe than meets the eye. The rotation of galaxies also creates their beautiful spiral structure. Spiral galaxies like the Milky Way have graceful arms that wind outward from the central bulge, arms that appear bright because they're filled with young, hot blue stars and glowing clouds of gas. For a long time, astronomers puzzled over these spiral arms. If the galaxy rotates with different parts moving at different speeds, the spiral arms should wind up tighter and tighter over time, eventually wrapping around the center like thread on a spool. But galaxies are billions of years old, and their spiral arms are still well-defined, not wound into tight spirals. Something must be maintaining the spiral structure despite the differential rotation. The answer turned out to be that spiral arms aren't fixed structures, they're not the same stars all the time. Instead, spiral arms are density waves, regions where stars and gas are temporarily compressed as they orbit through the galaxy. It's like a traffic jam on a circular highway. The traffic jam itself, the region of dense, slow-moving traffic, stays in roughly the same location, even though individual cars are constantly entering the jam from behind and leaving it ahead. The jam is a wave in the traffic, not a fixed group of cars. Similarly, spiral arms are waves in the distribution of stars and gas, not permanent structures. As stars and gas orbit the galaxy, they move into and out of these density waves. When gas clouds enter a spiral arm, they get compressed by the higher density of matter there. This compression can trigger the collapse of gas clouds and the formation of new stars. This is why spiral arms appear bright and blue. They're full of newly forming stars, young massive stars that burn hot and blue but have short lifespans. By the time these stars orbit out of the spiral arm, they've often already died. The spiral pattern persists because new stars keep forming in the arms, even as individual stars move through them. This elegant solution, that spiral arms are waves rather than fixed structures, shows how rotation at different speeds can create lasting patterns. The differential rotation that would seem to destroy structure actually maintains it through the physics of density waves. It's a beautiful example of how complex, ordered patterns can emerge from simple physical laws acting over cosmic timescales. Beyond individual galaxies, rotation manifests at even larger scales. Galaxy clusters, groups of hundreds or thousands of galaxies bound together by gravity, also show rotational motion, though much slower than the rotation of individual galaxies. The largest structures in the universe, superclusters and cosmic filaments, may show extremely slow rotational motions, though measuring these is challenging because the rotation periods are billions of years long. Even the universe as a whole might rotate, though this remains highly speculative and controversial. Einstein's general theory of relativity allows for solutions where the entire universe rotates, and some physicists have searched for evidence of such rotation by looking for patterns in the cosmic microwave background radiation, the faint glow left over from the Big Bang. So far, no convincing evidence for universal rotation has been found. The universe appears to be expanding uniformly in all directions without any overall rotation. But the question remains open, a reminder that even at the largest scales imaginable, we're still asking, does it spin? Returning to smaller scales but still cosmic ones, rotation plays a crucial role in one of the most extreme objects in the universe, black holes. Black holes form when massive stars collapse at the end of their lives, crushing all their matter into an infinitesimally small point called a singularity, surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. When a star collapses to form a black hole, it carries its angular momentum with it. Conservation of angular momentum means that as the collapsing star shrinks, it spins faster and faster, just like an ice skater pulling in her arms. The result is that most black holes are rotating, often at tremendous speeds. These rotating black holes, described by the Kerr solution to Einstein's field equations, have fascinating properties. The rotation drags spacetime itself around the black hole in an effect called frame dragging or the lens stirring effect. Near a rotating black hole, space itself is being pulled around in the direction of the black hole's rotation. If you tried to hover in one spot near a rotating black hole, you'd find it impossible. You'd be dragged along with the rotating spacetime, forced to orbit even if you weren't falling in. Rotating black holes also have a region called the ergosphere, just outside the event horizon, where the frame dragging is so strong that nothing can remain stationary, everything must rotate along with the black hole. In principle, it's possible to extract energy from a rotating black hole through processes that occur in the ergosphere, stealing some of the black hole's rotational energy. This is called the Penrose process, and while it seems like science fiction, it's allowed by the laws of physics. Some astronomers think that the enormous energy output from quasars, supermassive black holes at the centers of distant galaxies, the brightest objects in the universe, might come partly from tapping into the rotational energy of spinning black holes. And so we learned our own galaxy, the Milky Way, is a giant spiral galaxy containing between 200 and 400 billion stars along with vast gas and dust clouds, all bound by gravity and all rotating around common center. When you look up at night seeing that misty light band stretching across heavens, band that gave our galaxy its name, you're looking edge-on through galaxy disk, seeing billions of distant stars combined light all spinning together in galactic rotation. We discovered Milky Way rotates but not like solid disk or spinning wheel, like Sun with differential rotation. Different galaxy parts rotate at different speeds. Pattern is surprising, revealing something profound about galaxy nature. Based on visible matter, stars and glowing gas clouds we can see, astronomers expected regions farther from galactic center would rotate more slowly, just as outer planets orbit more slowly than inner planets, what Newton's laws predict, farther from gravitating mass, weaker pull, slower orbital motion. We found when astronomers measured actual rotation speeds of stars and gas clouds at different galactic center distances, found something unexpected. Instead of slowing down with distance, rotation speed remained roughly constant out to visible galaxy edge and perhaps beyond. Outer region stars moving much faster than they should based on visible matter. This flat rotation curve was one of first clear evidence pieces for dark matter, mysterious invisible matter that doesn't emit or absorb light but exerts gravitational influence. We learned astronomer Vera Rubin, working in 1970s, was instrumental establishing this result through careful galaxy rotation curve observations. What she and others found: galaxies must be embedded in enormous dark matter halos extending far beyond visible disk. Dark matter provides additional gravitational pull needed to keep outer stars moving as fast as they do. Without dark matter, galaxies would rotate differently. Outer stars would actually be flung away into space, rotation speeds too high for visible matter alone to hold them in orbit. Fact that galaxies hold together despite fast rotation tells us most galaxy mass is invisible to us, detectable only through gravitational effects. We discovered this discovery transformed universe understanding, means stars, gas, dust we can see, everything telescopes detect, represents only about 15% of total galaxy matter, other 85% is dark matter, doesn't interact with light at all. Still don't know what dark matter is made of despite decades of searching, one of modern physics' greatest mysteries. But existence revealed through rotation, through way galaxies spin. Rotation tells us there's far more to universe than meets eye. We found galaxy rotation also creates their beautiful spiral structure. Spiral galaxies like Milky Way have graceful arms winding outward from central bulge. Arms appear bright because filled with young hot blue stars and glowing gas clouds. Long-time astronomers puzzled over spiral arms. If galaxy rotates with different parts moving at different speeds, spiral arms should wind up tighter and tighter over time, eventually wrapping around center like thread on spool. But galaxies billions of years old and spiral arms still well-defined, not wound into tight spirals. Something must maintain spiral structure despite differential rotation. We learned answer: spiral arms aren't fixed structures, not same stars all the time. Instead, spiral arms are density waves, regions where stars and gas temporarily compressed as they orbit through galaxy. Like traffic jam on circular highway, traffic jam itself, region of dense slow-moving traffic, stays in roughly same location even though individual cars constantly entering jam from behind and leaving ahead. Jam is wave in traffic, not fixed car group. Similarly, spiral arms are waves in star and gas distribution, not permanent structures. We discovered as stars and gas orbit galaxy, move into and out of density waves, when gas clouds enter spiral arm, get compressed by higher matter density there, compression can trigger gas cloud collapse and new star formation. Why spiral arms appear bright and blue, full of newly forming stars, young massive stars burning hot and blue but with short lifespans. By time these stars orbit out of spiral arm, often already died. Spiral pattern persists because new stars keep forming in arms even as individual stars move through them. Elegant solution showing rotation at different speeds can create lasting patterns. Differential rotation that would seem to destroy structure actually maintains it through density wave physics. We found beyond individual galaxies, rotation manifests at even larger scales. Galaxy clusters, groups of hundreds or thousands of galaxies bound by gravity, also show rotational motion, though much slower than individual galaxy rotation. Largest universe structures, superclusters and cosmic filaments, may show extremely slow rotational motions, though measuring challenging because rotation periods billions of years long. We learned even universe as whole might rotate, though remains highly speculative and controversial. Einstein's general relativity allows solutions where entire universe rotates. Some physicists searched for evidence of such rotation by looking for cosmic microwave background radiation patterns, faint glow left over from Big Bang. So far, no convincing evidence for universal rotation found. Universe appears to be expanding uniformly in all directions without overall rotation, but question remains open. Reminder that even at largest imaginable scales we're still asking, does it spin? We discovered returning to smaller but still cosmic scales, rotation plays crucial role in one of universe's most extreme objects, black holes. Black holes form when massive stars collapse at life's end, crushing all matter into infinitesimally small singularity points surrounded by event horizon, boundary beyond which nothing, not even light, can escape. When star collapses, forming black hole carries angular momentum with it. Conservation of angular momentum means as collapsing star shrinks, spins faster and faster, like ice skater pulling in arms. We found result as most black holes are rotating, often at tremendous speeds. These rotating black holes described by Kerr solution to Einstein's field equations have fascinating properties. Rotation drags spacetime itself around black hole, an effect called frame dragging or lens-stirring effect. Near rotating black hole, space itself pulled around in black hole's rotation direction. If you tried to hover in one spot near a rotating black hole, would find it impossible. You'd be dragged along with rotating spacetime, forced to orbit even if not falling in. We learned rotating black holes also have ergosphere region just outside event horizon where frame dragging so strong nothing can remain stationary. Everything must rotate along with black hole. In principle, possible to extract energy from rotating black hole through processes occurring in ergosphere, stealing some black hole's rotational energy, called Penrose process. Seems like science fiction but allowed by physics laws. Some astronomers think enormous energy output from quasars, supermassive black holes at distant galaxy centers, universe's brightest objects, might come partly from tapping spinning black holes' rotational energy. Each fact a gentle reminder of rotation's cosmic reach. From galactic spirals to the universe's largest structures, from dark matter's invisible grip to black holes dragging spacetime itself. Everything spinning at every scale, rotation revealing hidden truths about the cosmos, dark matter through flat rotation curves, spiral structure through density waves, even the nature of spacetime through frame dragging. Rest in this cosmic dance now. This recognition that rotation is written into the fabric of reality at every scale. Galaxies wheeling through space, black holes spinning so fast they drag reality itself, all following the same conservation laws that govern the skater's spin and the Earth's turn. Let yourself drift with these vast cosmic rotations, these spirals and spins spanning light years and eons, peaceful and unhurried, carried gently towards sleep. As we approach the end of our peaceful journey through the science of rotation, we arrive at the smallest scales of reality, where we discover that the principle of spin continues all the way down to the fundamental particles that make up matter itself. Even at the quantum level, where the familiar laws of classical physics give way to stranger rules, rotation, or something very much like it, remains a fundamental property of nature. In quantum mechanics, elementary particles like electrons, protons, and neutrons possess a property called spin. Despite the name, this isn't quite the same as the rotation of a planet or a galaxy. An electron isn't literally a tiny ball spinning on its axis. Quantum spin is an intrinsic property of particles, more like a fundamental characteristic such as mass or electric charge. Yet the mathematics of quantum spin closely resembles the mathematics of angular momentum, the measure of rotational motion we've been discussing throughout this journey. Quantum spin was discovered in the 1920s through a series of elegant experiments, most famously the Stern-Gerlach experiment conducted in 1922 by Otto Stern and Walther Gerlach. They passed a beam of silver atoms through a non-uniform magnetic field, expecting that atoms with different orientations of their internal magnetic properties would be deflected by different amounts, creating a continuous spread of positions. Instead, they found something astonishing. The beam split into just two distinct beams, as if each atom could only exist in one of two states, spin up or spin down. This was one of the first direct demonstrations that quantum properties are quantized. They come in discrete values rather than continuous ranges. An electron's spin, for instance, can only be found in one of two states when measured, spin up or spin down, sometimes called spin plus 1/2 and spin minus 1/2. There are no in-between values, no electron spinning at 3/4 speed or 1/4 speed. This quantization of spin is fundamentally different from the rotation of everyday objects, which can spin at any speed. But like classical angular momentum, quantum spin is conserved. The total spin in a closed system cannot change, just as the total angular momentum of rotating classical objects is preserved. The conservation of quantum spin has profound implications. When particles interact, when they collide, decay, or combine, the total spin before the interaction must equal the total spin after. This constraint governs which interactions are possible and which are forbidden. Nuclear reactions, particle decays, the fusion processes in the cores of stars, all must conserve spin. This makes spin conservation one of the fundamental bookkeeping rules of the quantum world, a constraint that shapes the behavior of matter at its most basic level. Quantum spin also determines many of the properties we observe in everyday matter. Electrons are fermions, particles with half-integer spin, spin 1/2. A crucial property of fermions is that no two identical fermions can occupy the same quantum state simultaneously. This is called the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle is why matter has structure and solidity. When atoms come together to form molecules or solids, the electrons can't all collapse into the lowest energy state because each state can only hold one electron of each spin orientation. They must fill up higher energy levels, creating the chemical bonds and electronic structure that give different materials their distinctive properties. Without the Pauli exclusion principle, without the quantum spin that makes it necessary, all electrons would collapse into the lowest possible energy state, and matter as we know it couldn't exist. There would be no chemistry, no complex structures, no life. The fact that electrons have spin 1/2, making them fermions subject to the exclusion principle, is why atoms have size, why different elements have different chemical properties, why you can't pass your hand through a table. In a very real sense, the solidity of matter is a consequence of quantum spin. This has a beautiful connection to rotation at larger scales. Remember how we discussed that planets and stars form from rotating clouds of gas collapsing under gravity? At the quantum level, something similar prevents complete collapse. When atoms are compressed together, the exclusion principle eventually creates a pressure, called degeneracy pressure, that resists further compression. This pressure doesn't come from heat or motion in the usual sense. It comes purely from the quantum mechanical requirement that fermions can't occupy the same state. Degeneracy pressure is what holds up white dwarf stars, the remnant cores of stars like our Sun after they've exhausted their nuclear fuel. When the Sun dies billions of years from now, it will shed its outer layers and leave behind a white dwarf about the size of Earth but with about half the Sun's mass. This incredibly dense object, a teaspoon of white dwarf material would weigh several tons, is prevented from collapsing further by electron degeneracy pressure. The electrons are packed so tightly that they can't be compressed anymore without violating the Pauli exclusion principle. In effect, the quantum spin properties of electrons are what keeps dead stars from collapsing completely. For even more massive stellar remnants, electron degeneracy pressure isn't enough. If a dying star's core is massive enough, more than about 1.4 times the Sun's mass, a limit called the Chandrasekhar limit, the gravitational force overcomes electron degeneracy pressure, and the core collapses further. The electrons are forced to combine with protons, forming neutrons, and the result is a neutron star, an object even more extreme than a white dwarf, with all the mass of a star compressed into a sphere only about 12 miles across. Neutron stars are held up by neutron degeneracy pressure. Neutrons, like electrons, are fermions with spin 1/2, so they too obey the Pauli exclusion principle. The neutrons in a neutron star are packed as tightly as quantum mechanics allows, creating a pressure that balances gravity and prevents further collapse. A teaspoon of neutron star material would weigh about 1 billion tons. These objects are so dense that a sugar cube-sized piece would have more mass than all of humanity combined. And neutron stars rotate. In fact, many neutron stars rotate incredibly rapidly. When a star collapses to form a neutron star, conservation of angular momentum means that the rotation rate increases dramatically, just as we've seen with ice skaters and collapsing gas clouds. A star that was rotating once every 30 days or so might, after collapsing to a neutron star, rotate hundreds of times per second. The fastest known pulsar, a rotating neutron star that emits beams of radio waves like a cosmic lighthouse, spins 716 times per second. That's a city-sized object, more massive than the Sun, completing more than 700 full rotations every single second. These rapidly rotating pulsars are among the most precise clocks in the universe. Their rotation is so stable that astronomers can predict when their radio pulses will arrive with extraordinary accuracy, sometimes to better than a microsecond over years of observation. This precision comes from the fact that neutron stars have so much rotational inertia, they're so massive and compact that once spinning, almost nothing can change their rotation rate. They slowly spin down over millions of years as they lose energy to radiation and magnetic fields, but the slowdown is gradual and predictable. The study of pulsars has taught us much about rotation in extreme conditions. Some pulsars are in binary systems, orbiting another star, and their orbital motion combined with their rapid rotation creates complex effects that test Einstein's general relativity in a strong field regime. Other pulsars show glitches, sudden tiny increases in rotation rate that occur when the neutron star's crust suddenly rearranges, like an earthquake but on a star. These glitches reveal that neutron stars have complex internal structures despite being smaller than cities. Beyond neutron stars lies one final state, If a stellar remnant is too massive even for neutron degeneracy pressure to support, nothing can prevent total collapse. The object collapses past the neutron star stage into a black hole, where, as we discussed earlier, rotation creates frame dragging in the ergosphere. This represents the ultimate expression of rotation's power, so much angular momentum compressed into so small a space that it literally drags the fabric of spacetime around with it. And so our journey through the science of rotation comes to its end, though rotation itself continues everywhere, at every scale, forever. We've traveled from the ancient observations of the wheeling heavens, through Galileo's insight about relative motion, to Foucault's pendulum making Earth's spin visible. We've understood how the solar system formed from a rotating cloud, how angular momentum is conserved from collapsing nebulae to spinning skaters, how tidal forces lock moons and gradually slow planets. We've seen how rotation shapes worlds into oblate spheroids, how it generates protective magnetic fields through dynamo action, how differential rotation creates the solar cycle and maintains spiral galaxy arms. We've discovered that most of the universe is invisible dark matter, revealed only through the unexpected rotation of galaxies. We've learned that black holes spin so fast they drag spacetime itself, that the smallest particles have quantum spin governing the structure of matter, and that neutron stars rotate hundreds of times per second, held from collapse by quantum mechanics. Through it all, one principle has remained constant: the conservation of angular momentum. What spins tends to keep spinning. What rotates will continue to rotate unless acted upon by an external torque. This simple law connects everything we've discussed, from planets to galaxies, from electrons to black holes. It explains why things spin in the first place, because the universe started with rotation, with small motions and asymmetries, and as matter collapsed under gravity, those rotations amplified, creating the spinning cosmos we see today. We live in a rotating universe. The Earth spins beneath you at 1,000 miles per hour. The Earth and Moon dance around their common center of gravity. The Earth-Moon system orbits the Sun at 67,000 miles per hour. The Sun and all the solar system's planets orbit the center of the Milky Way galaxy at 514,000 miles per hour. The Milky Way rotates, taking 225 million years to complete one galactic rotation. The last time we were at this point in our orbit, dinosaurs were just beginning to evolve. And you are part of this cosmic dance. The atoms in your body were forged in the cores of rotating stars, ejected into space when those stars died, incorporated into the rotating cloud that became our solar system, assembled into you on this rotating planet. The very electrons that make up your atoms have quantum spin. The proteins in your cells, the DNA that encodes your genes, even these have handedness. They're chiral, existing in mirror image forms that rotate polarized light in different directions. Rotation is not something separate from you, something happening out there in space. You are made of rotation, shaped by rotation, carried by rotation. Even as you lie still, you are spinning with the Earth, orbiting with the solar system, wheeling through the galaxy. You are a temporary eddy in the cosmic flow, a brief pattern of organized matter maintained by rotation and energy, a conscious witness to the universe's eternal turning. As you rest now, drifting towards sleep, recognize that you are being carried on all these nested rotations: Earth's daily spin, its yearly orbit, the solar system's galactic motion. You are safe in this cosmic dance, held by forces that have been operating for billions of years and will continue for billions more. There's nothing you need to do, nowhere you need to go. The universe is turning, patient and eternal, and you turn with it. Let the ancient rhythm of rotation carry you now into sleep, into dreams, into the mystery of consciousness fading and returning. Feel the earth turning beneath you, gentle as a mother rocking a child, steady as the stars wheeling overhead. Billions of years this rotation has continued, and billions more it will persist, and tonight it carries you peacefully into rest. Everything spins. Everything turns. And in that turning is a kind of perfection, a cosmic dance that includes everything that is, was, or ever will be. You are part of that dance, held in rotation's gentle embrace, safe and whole and exactly where you need to be. Rest now. The universe continues its turning. You can let go, drift, sleep, carried by rotations older than time, by forces that shaped the cosmos and shaped you. There's profound peace in this, in being part of something so vast, so ancient, so perfectly balanced. Good night. Sleep well. The universe turns on, and you turn with it, peaceful and complete.